arc length of a curve. Okay, suppose we have a curve y equal fx. We want to find the length of this curve from A to B. Then what we do this problem is we locally approximate this curve by its tangent line or a line, a straight line. Then we find the main part of this arc length by this straight line. And then we find third s, okay, third s, which is the approximation of the differential ds. And then once we do that, then we find the main part ds, okay, the arc length element. If you factor out this third x, then what essentially you use is actually square root of 1 plus derivative squared dx. So this is the arc length element. Then we integrate the element to cancel the d to antiderivative so that we get the arc length, okay. And we did several examples of this arc length. And we mentioned one last time the problem arc length of the ellipse of an ellipse is related with some important topic which is called elliptic integrals. And this topic is really huge. You can talk this kind of elliptic curves, elliptic integrals for several years, okay, without, you know, every time you can have new material. This is a huge topic, okay. We will not talk about that thing, okay. It's beyond the scope of this course. However, this is actually a really important thing in mathematics, the elliptic integral. Okay, what we do today is we will continue several examples of this computation of curves. We will give some examples. Okay, now let's do some examples. Okay, let's see this example. The curve is given by y equals ln x, cosine x. Here, the x value is from 0 to power 3. Find its arc length. Find the length of the curve. Find the length of the curve. The curve. Okay. So we first differentiate dy over dx. Dy over dx. Now, if we differentiate the thing, so we take a derivative dx ln cosine x. We use logarithmic differentiation. Then what we get is we flip cosine. Now cosine derivative get negative sine x. Okay, so this we get this negative tangent x. Okay, then ds, we write down ds. ds is 1 plus dy over dx squared dx. Now this will be 1 plus negative tangent x squared dx. So this will be 1 plus tangent squared dx. And 1 plus tangent squared, which is tangent secant squared. And then we get this should be secant x dx. Okay, here secant is positive. Our x is from 0 to power 3. Okay, secant x is positive. So we can write down. Okay, ds is the thing. So s we integrate the thing. We integrate ds from 0 to power 3. Remember, secant derivative, antiderivative is ln secant x plus tangent x. Okay, by fundamental theorem of calculus. Okay, this will be ln, plug in secant power 3 plus tangent power 3. Subtract ln secant 0 plus tangent 0. Now secant power 3 is 1 over cosine power 3. Cosine power 3 is 1/2. Okay, so this is 2 plus tangent power 3, which is root 3. Okay, so this will be ln thing minus secant 0, 1 over cosine 0. Okay, cosine 0 is 1. Cosine 0 is 1. So this tangent 0 is 0. So this is ln 1. Ln 1. Ln 1 is just 0. So we finally see this is ln 2 plus root 3. Okay, 2 plus root 3. Then we're done. Then we're done. Okay. Okay. More example. Y equals ln x. Y equals ln x. Here x is from 0 to root 3. Okay, now we find dy over dx. dy over dx, which should be ln x derivative, which is 1 over x. Okay, then arc length element, this will be 1 plus dy over dx squared. So this will be 1 plus 1 over x squared. This will be here x is positive. This will be this. Then we integrate. S will equal to 0. X is from 1 to root 3. X 1 plus x squared dx. And then here we use trig substitution. Okay, trig substitution. So we let x be tangent theta. Okay, tangent theta. Then we see by our trig substitution 1 plus x squared. This will be 1 plus tangent squared, which will be secant theta. Now dx will be tangent derivative. We get secant squared d theta. Okay, so this will be theta is from x is a 1. Then we get tangent theta is 1. Theta is pi over 4. When x is root 3, which implies tangent theta is root 3. This implies theta is pi over 3. Okay, so this is actually pi over 4 to pi over 3. My fundamental theorem calculus was change, switch everything, substitute everything. So this will be secant theta. Now dx will be secant squared theta. Now x will be tangent theta. Okay, now what do we do? Now we what we do is we substitute the thing by, what do we do? We substitute the thing, everything by sine and cosine. So this will be 1 over cosine. This will be sine over cosine. This will be 1 over cosine squared d theta. So this will be, it's complicated, this example. Let's just pi over 4 to pi over 3. Okay, so this will be cancel a factor of cosine. So it's sine theta, cosine square of theta, d theta, from pi over 3 to pi over 4. Okay, so once we have odd, then we substitute odd. Okay, so let t be sine theta. Okay. What did we do? Okay, sorry, we substituted the even part. We substituted the even part, cosine theta. Then this will be This will be t squared. Then dt will be sine theta, d theta. All right. So this will be, let's do it in this manner. Sine theta, d theta, sine squared, cosine squared. Okay, so this will be pi over 4 to pi over 3. This thing will be, let's substitute. So this will be dt, negative dt. This will be t squared. This will be 1 minus t squared. T is cosine, so this will be root 2. This will be cosine, this is 1/2. Okay. Okay, so finally it will be, after substitution, now this -1 cancels that thing. Switch upper limit with the lower limit. So this is 1/2 to root 2 over 2. dt over 1 minus t squared times t squared. Then we use partial fraction decomposition. This requires a lot. Partial fraction decomposition. So 1 minus t squared times t squared. What is this thing? So partial fraction decomposition. So this will be so you can write anything as a thing. AB plus this should be what should be this partial fraction decomposition? Let's see if we can we have a quicker way. So this will be let's see. Let's check. Yeah, this actually is the partial fraction decomposition. You can easily check. This is easy to check. It's easy to check. This thing you write as 1 minus t, 1 plus t. Okay, so this will be 1 plus t plus 1 over t squared. And then the thing you divide by 1/2. Okay, so check this partial fraction decomposition. Check this partial fraction decomposition. Then we have this thing is, it's complicated now. Okay, so this will be 1/2 to root 2 over 2. 1/2 1 minus t plus 1 plus t plus 1 over t squared dt. Okay, so finally this will be find its antiderivative 1/2 ln 1 plus t minus ln 1 minus t plus subtract 1 over t, then from 1/2 to root 2 over 2. Okay, finally then we are done. Okay, so this is the 1/2 ln 1 minus t over, so it's when t is root 2 over 2, so it's the 1 plus root 2 over 2 minus 1, okay, minus root 2. When t is 1/2, minus 1/2 ln 1 plus 1/2, 1 minus 1/2, minus when t is 1/2, this is the 2. Okay, wow. So finally we see this is very complicated now. So this is cancel the factor 2. Okay, so this will be 1/2 ln 1 plus root 2, 1 minus root 2, minus root 2, minus 1/2 ln 3 plus 2. And this is actually ln is, if you multiply denominator by, so if you rationalize denominator, this thing will be multiply denominator numerator by 1 plus root 2. Okay, what I did, sorry, it's 2. So if you cancel root 2, this will be 1 plus root 2 or root 2 minus 1. So this will be root 2 plus 1 squared. So this will be ln 1 plus root 2 minus root 2 minus 1/2 ln 3 plus 2. Okay, so this is the arc length of this curve. It's very tedious for this example. Okay, any questions? Any questions? Okay, let's see another example. Okay, y equals ln e to the x plus 1 e to the x minus 1. Here, x from a to b. A is positive. Okay, now we find derivative. Okay, so this is ln e to the x plus 1 minus e to the x minus 1. So dy over dx, we differentiate. Take the derivative. Okay, so this will be so what does this be? This will be a common denominator. Okay, so finally this will be if you cancel denominator, so this e to the 2x minus e to the x minus e to the 2x minus e to the x over e to the 2x minus 1. Okay, so finally this will be negative twice e to the x over e to the 2x minus 1. Okay, so dy over ds, this will be 1 plus dy over dx squared times dx. So this will be 1 plus 2 e to the x, e to the 2x minus 1 squared dx. Okay, so this will be 1 plus e to the 2x squared. This is 4 e to the 2x. Okay, dx. Now use common denominator. Dx. Okay. Then we take off the bracket, expand. So this is the actually if you expand, you will see this is negative. Okay, squared times twice e to the 2x plus 1 okay, plus 4 e to the 2x. Okay, that's perfect. So here minus 2 plus minus 2 e to the 2x plus 4 e to the 2x. Now this then you get this thing over e to the 2x minus 1 squared dx. This finally you see this is e to the 2x squared plus e to the 2 to the x, e to the 2x plus 1. And this is actually a perfect square. This is a perfect square. Now this is perfect. Okay, the denominator is perfectly square. So it's e to the 2x plus 1 squared over e to the 2x minus 1 squared. If you take a square root, and then you see this is e to the 2x plus 1 e to the 2x minus 1 dx. Okay, so you get a rational function of e to the 2x. Then this you get ds. Then you get s is a to b ds e to the 2x plus 1 is here plus 1 e to the 2x minus 1 dx. And then we need to do substitution. Okay, substitution. How do we do this? Evaluate this. Okay, so this will be, let's see. Once we have this thing, what we usually do is we use substitution. Okay. What substitution do we use? What substitution do we use? Okay, in this situation, what we substitute is e to be, e to the x or e to the 2x. Okay, this is the usual substitution that we use. Okay. Okay, let's see if we do let's see if we do e to the 2x. Let's do e to the 2x. So this will be, let t to be e to the x. Then this will be, find antiderivative first. This is t squared minus 1, t squared plus 1. Dx, dt is e to the x dx. So dx will be t dt. Then what we do is we use partial fraction decomposition. Partial fraction decomposition. Okay, partial fraction decomposition. This will be partial fraction decomposition. Now we should do partial fraction decomposition. So we have this t minus 1, t plus 1 times t squared plus 1. This is partial fraction decomposition. We use partial fraction decomposition. Now let's use partial fraction decomposition. So this will be linear factor. Okay, it has a product of linear factor, distinct linear factors. Then this we get t squared plus 1. This will be a times t cancel denominator plus c c times t minus 1 t plus 1. Then we take t to be 0. Take t to be 0. Take t to be 0. Then we get 1 equal to t is 0. Then we get 0 plus 0. T is 0. Plus this term, the last term is negative c. C times negative 1 times 1. So this is negative c. So c is negative 1. Okay. Now take t to be 1. Take t to be 1. Then we get the left side is 1 squared plus 1, so it's 2. This is 2a. This is 0. This is 0. So a is 2. A is 1, sorry. And then take t to be negative 1. Take t to be negative 1. Then we get 2 equal to t is negative 1. T plus 1 is 0. Okay, so term a is 0. Plus this is the negative 1. Negative 1 minus 1, negative 2 times negative 1. So it's 2b plus 0. So again, we get a b is 1. Okay, so finally, it's not too bad, partial fraction decomposition. So we get this thing is t squared plus 1 over t squared minus 1 times t. This equal to 1 over t minus 1 plus 1 over t plus 1 plus 1 minus c is okay. Okay, then we can evaluate this integral now. Then we can evaluate this integral. So this will be, its antiderivative will be, this will be dt, dt. So we find its antiderivative. So this will be ln, did I get a mistake? Ln, this is right, t minus 1 plus ln t plus 1 minus ln of t. T is positive. T is positive. Okay. So it's a ln t squared minus 1 over t. Yeah. Okay, so finally we recover to go back to original function. T is e to the x. T is e to the x. So it's a ln e to the 2x minus 1 over e to the x. So if you see, this is ln e to the x minus e to the negative x. More symmetric thing. So we find antiderivative. We find antiderivative. Okay, so we find antiderivative. So S will be by fundamental theorem of calculus ln e to the x minus e to the negative x, a to b. Okay, a to b, a to b. Now a is positive, b is greater than, a is positive. Okay, so this plugging a and b. This ln e to the b minus e to the negative b over subtract that thing, you divide e to the a minus e to the negative a. Okay. Then we're done for this curve. Okay, any questions about this problem? Okay. All right. Now let's talk about another topic. Talk about another problem. Okay. Talk about how to the history of the pi. Now we know the example. Suppose we have a circle. So let me see. Let me insert a circle. Insert a circle. Okay, how do I insert a circle? Draw. Okay, yeah. Okay, suppose we have a circle. Now its length is 2 pi r. There's no 2 pi r. Now r is 1. Length is 2 pi. 2 pi r is just 2 pi. Now suppose we don't know how big pi is. How do we compute 2 pi without the idea is we use polygons. The idea is in the early history, people compute pi is we use polygons. Okay, polygons to approximate a circle. Idea. Use polygons to approximate the circle. Okay. Okay. Now suppose we do maybe let's do hexagon maybe. We choose some smaller number n-gon. Now suppose we do a hexagon. Do a hexagon. Okay, do a hexagon. Okay, suppose we do a hexagon. Okay, do a hexagon. Then the perimeter of this hexagon, then possibly the perimeter of this hexagon. Find the perimeter of this hexagon. Find the perimeter of this hexagon. How do we find? Find the perimeter of a regular n-gon. Okay, for this problem, we are dealing with hexagon, i.e. 6. We have 6 sides. Then you see here, first, what is this angle? The angle theta is the central angle. The central angle is, the total angle is 2 pi, but it is an angle. So this is actually 2 pi over n. 2 pi over n. Now for this example, n is 6. Okay, n is 6. Okay, because we have 6 sides. For general angle, this is the 2 pi over 6, 2 pi over n. Central angle. Theta is 2 pi over n. Okay, so this is radius r. And then if you do this thing, solve this 90-degree triangle. Okay, so you find this thing by solving right triangle AB. Let's use AB. Here, this is M, the midpoint. Then you see MB is exactly the opposite of the half theta. Okay, half theta. So it's half in this right triangle. This is a half of theta. This is M. This is the O, center O. This is B. In the triangle OMB, we solve this right triangle. Solve this triangle. So this is 1. Hypotenuse 1. So MB over OB is opposite over hypotenuse, which is sine the angle NO. Okay, theta over 2. So OB is 1. OB is 1. So we get MB is sine half of theta. Okay, which is theta. Remember, theta is 2 pi over n for regular angle. So this is sine pi over n. Sine pi over n. Okay, sine pi over n. Sine pi over n. So then the parameter of a regular angle is, so AB. Then AB is twice MB. This will be 2 times sine pi over n. Okay. Then the perimeter. Then we have n sides. Each side is equal, congruent. So then we get the perimeter of regular angle. Regular angle is now in the unit circle. Angle inscribed in the unit circle. In the unit circle is 2n sine pi over n. Okay, pi over n. Okay. Now, what happens if we some special example? So this inscribed angle. Now, how about the this case? Now here we are actually underestimate. Okay, if you see the perimeter of this regular angle is less than the arc length of the circle, 2 pi. Okay, so we are actually underestimate. Okay. How do we compute this area? How do we compute the area? Area of a regular angle. This area. How do you compute this area? Now we break it into n triangles. Okay, we break it into n triangles. Now each triangle we can find. So we break it into n triangles. So this is the R. This is the height. This is R. Then this side is n times. So this is the theta over 2. Okay. A, B, M, O. Then we can find EM. EM is, we already know, EM is sine pi over n. Sine theta over 2. So the height, H is cosine. Cosine is the thing. Okay, height is the thing. Cosine. Then area. So the area will be twice 1/2 sine theta times cosine theta. Okay, base times height. Base times height. And then we need to multiply the thing by 2. So we get a triangle. Okay, triangle AB, AOB. Okay, AOB. Then we multiply how many triangles are there? N triangles. Okay, so we finally see this is by double angle formula. Then this will be n times sine theta over 2 cosine theta over 2. So this is actually n over 2 sine theta, which will be n over 2 sine 2 pi over n, sine 2 pi over n. Okay. Okay. Now let's talk about the this case. Suppose we have a circle. Now the area is underestimated. The area is underestimated. So this is less than pi. This is less than pi. Now suppose we do. Okay, this is not what I want. Okay, now suppose we do exterior polygons. Suppose we have a polygon, but it's a exterior. So again, let's do the 6gon for convenience. Okay. Okay. Now what we do is we use this. We overestimate. Okay. Plot tangent line. So the circle is actually inscribed in a regular n-gon. The circle is inscribed in n-gon. Okay. Now, how do we find its area? Okay. Let's plot. Okay, how do we find its area? Okay, so we have this case. How do we find its area and the perimeter of this n-gon? For this, we get a x-gon. Okay. Once again, we use geometry. Once again, we use geometry. We use geometry. Okay. Okay, let's see the geometry. We solve the triangle. We solve the triangle. Here, this is again theta. This angle is theta. Theta is 2 pi over n. So it's n gon. Okay, 2 pi is divided by 2 and divided by n. Now to find this area, what is y? The height is actually y. This part is y. The height is radius. This is the height is radius y. So if you do the triangle, so this think out a triangle. This OAB. The height is actually y. The height is y. So this is actually theta over 2. Theta over 2. Now this thing will be tangent. Okay, tangent theta over 2. The thing will be tangent theta. Area will be what? Area will be triangle ABC. Triangle AOM. Let's use AOM. Triangle AOM will be 1/2 times base times the half theta times y. Okay, times y. But here, how many triangles do we have? So we get a triangle area of the n-gon. Area of this n-gon. So we get an n-gon area of n-gon. Regular n-gon, okay? Regular n-gon with the unit circle inscribed, okay? Inscribed in this n-gon. So this will be multiply this thing by 2n. Then we get this thing is n times tangent theta over 2. This will be n times tangent. Theta is 2 pi over n. So this is the pi over n. Pi over n. Pi over n. Then you see this is the overestimated. Okay, now then we can use this overestimated and underestimated to get a better approximation to the average, such that we get the area. We get an area. A more precise area. For instance, if we do this. Okay, I want to choose it to be an 8-gon. Octagon. An octagon inscribed. An octagon inscribed in how is the area? What is the area? What is the area of an octagon? Octagon is area inscribed in a circle, in the unit circle. Its area has area. We take n to be 8. Okay, n is 8. N is 8. So we get then its area will be 4 times. You see, plugging this thing. Okay, this is what we want. Plugging in by 8. So we get a 4 times sine 2 pi over 8. So we get a 4 times sine pi over 4. Then we get, this is the 4 times root 2 over 2. So we get a twice root 2 over 2. Okay, twice root 2 over 2. And then we do this. For the exterior regular n-gon, we choose n to be 6. Choose n to be 6. The area of the exterior, or area of the n-gon, with circle inscribed. Okay. Inscribed. So inside, so this will be, use this formula. Okay, use this formula. Okay, we choose n to be 6. This will be 6 times tangent 6 over pi. Okay, so what do we get? 6 times tangent pi over 6. What do we get? Tangent pi over 6. What do we get? Tangent pi over 6 is root 3 over 3. Then we get twice root 3. Okay. Now, if we, so here, this is overestimated. Estimated. This is twice root 2 or twice root 2 is underestimated because this is inscribed in a circle. Okay. Now twice root 3 is overestimated on pi because in this case the circle is inscribed in the polygon. So the circle has area less than the polygon. Okay, it makes sense. Okay, underestimated. Now to get a better estimation, we just do the average. Okay, the average. Find the average. Average of this estimate. Overestimate plus underestimate is average. Okay, average. The average is root 2 plus root 3. So this is an approximation of pi. Now, if you notice, what is root 2? What is root 2? What's the decimal expansion of root 2? What's the decimal expansion of root 2? Root 2 is 1.414, etc., etc. Okay. Root 3, what's root 3? Root 3 is 1.732, etc., etc. Okay. Now, if you add them, what is pi? Pi is 3.141, etc., etc. Okay. Now, root 2 plus root 3. Have you noticed this? Root 2 plus root 3. If you add them together, so this will be 1 plus 1. You get 7 plus 4. The second digit, you get actually 1. What you see is this is a good estimation. So root 2 plus root 3 is a good approximation of pi. Okay. 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 This gives an approximation of pi. This gives an algorithm how to compute pi. Okay. Use area and use area of polygons. Okay. Use area of polygons. You can also use not use area, but use arc length. Use the parameter of a polygon to approximate the area, to approximate the length of this circle, 2 pi r. This also works. Okay. So this idea use polygons to approximate a circle is really important in modern mathematics. There's a subject called in number theory called cyclotomic field theory. Cycle means a circle. Tomic means cut. Okay, cyclotomic means cut a circle into n pieces. Okay, cut into n pieces. Very important. Okay, important. A branch. This is a branch of mathematics in number theory. So circles plays a really important role in mathematics. Okay, this is the idea of this this part, cyclotomic fields. Very important, very important. You may heard the story of Fermat-Last theorem. Fermat-Last theorem is actually related with this cyclotomic fields. Fermat-Last theorem, which is solved by Andrew Wiles. And okay, Fermat-Last theorem is related with this cyclotomic fields. Okay, now any questions? Any questions? Okay, let's go to the next section. Area of a surface of revolution. Area of a surface. The surface has some symmetry. It's obtained by some rotation. Okay. First, we start with an easy example. Suppose we have a cylinder. We find its surface area. Okay, a cylinder with open top and base. Okay, a cylinder with open top and base. So we find the side surface area of a cylinder. So suppose the circle, the base and top, they are circles. The radius of the circle is R. The radius is R. Okay, find the side surface area. Now, if we cut a cylinder, the surface will now, if you expand it, then this is what you get. Expanded. So this thing is 2 pi r. Okay, coming from the perimeter of the circle. Now this will be the height. The height h will be the height h. Okay, the height h. Okay, so the area of the rectangle will be 2 pi r base times height. Okay, base times height. Okay, now this turns out to be a special property for the cylinder. Now, if you have a general surface, now you may ask a question: in which situation, if you cut it and expand it such that you get a flat, you can flat it. Okay, for the cylinder, you can do that. You cut it, you can make it a flat. Okay, you can make it a flat as a surface. Now, if you have a ball, if you have a sphere, if you cut it, whatever, you cannot make the surface area flat. Now, this is actually an important question in differential geometry. Okay. Now, which asks us how to determine a surface if you can expand it by a flat. If you expand it, then you get a flat surface. I.e., how do you determine whether a surface is flat or not? This is a really important question in differential geometry. Okay, question. So this is a digression. Side correction. When a surface is flat. So important question, a question in differential geometry to be answered. If you study differential geometry, you will have a chance to see this problem. Okay, right now we just go back to our original question. Now, what is the surface area of a cone? What is surface area of a cone? Now, suppose we have a cone, not a cylinder. Now let's talk about this cone. Okay, now surface area, lateral surface area of a cone. Okay, this is length is L. Length is generating length of the generating line L. Okay, so if you cut this cone, and expand it, so this what you get is a sector. Okay, this what you get is a sector. Excuse me. What you get is a sector. What you get is sector. So if you write it, the sector will look like this. Expand this. So it will be a sector. If you cut along a generating line, okay, then it will be looks like this. Okay. See that. Now this is the line is here is L. This is L. This is L. Okay. So the angle theta. How do we determine the angle theta? Now the base is a circle. Its perimeter is 2 pi r, and its perimeter will be the arc length of this sector. Okay, 2 pi r. 2 pi r. So here this the radius of the base is r. Radius of the base is r. Then you see we can find theta. We can find theta. So then area of the sector will be 1/2 base times the height. You can view this as a right triangle, base times height, So this you can get is this is the pi r l. Okay, now let's do it through the general surface area by revolution. Okay, now suppose we have a function, we rotate it. Okay, example. So suppose we have a function. Maybe we do it like this. Now, if we rotate it with respect to x-axis, this is y equal fx. Then we rotate the thing with respect to x-axis. Then what we get is more like the thing. Rotate the thing. Now, what do we get here is, so this is A, this is B, this is B. Now, if we rotate it, it looks like this thing. Okay. Now this side we get the thing. Okay. Now we can see here. Okay. Now find the surface area of this object that we obtained. Find the surface area that we obtained. So we rotated the region. Okay, then we get a solid. Now, what's the surface area of the solid? Question. Find the the surface. I mean the side surface. The other the base and the top. They are both circles. They are easy to find. Find the side surface area. Side surface. side surface area of the solid. Okay. What we do is we cut a small pieces and see what determine the area. Okay. We cut a small pieces. Idea. Cut a same piece. And find the area element. Okay, if you cut a small piece, so let's suppose we cut a small piece. Maybe we just look like this. For a small piece, the curve fx, we assume that the function fx is nice, so that we can view it as a straight line. For a small piece, we can view it as a straight line. So okay, so this is what we get. Actually? So it's small, looks like a cylinder. But the base and the top, the radius is different. Okay. How should we do it? Find the side surface area. Okay, now actually what we need to do is we need use a cone. We cut something from a cone. What we do is so it's not a cylinder. We cannot view it simply as a cylinder. What we do is you see, what we do is actually cut it. If it's a parallel, then it's a cylinder. There's no problem. Then here, what we do is we complete it. So that said, we get a cone. Then we find the side surface area of a cone. Okay, then we do estimate. Okay. Now suppose we have this structure. Let's do this structure. So the top radius is R1. The base radius is R2. Then you can find its side surface area. How do you do it? Well, we do it by this thing. So we find this line, the intersection, completed to be a cone. Then this thing will be, suppose this is L. Okay, suppose this is L1. This part is L1. Then we use the geometry. R1, R2. So by geometry, R1 over R2 will be L1 over L1 plus L by similar triangles, by geometry. The two triangles are similar. Then we find the side surface area of the big cone. Remember, the big cone is pi r, the big L, L1 plus L, Okay, remember we just did the area of a cone, side surface area, which is pi RL, pi RL. L is the line, generating line, length of the generating line. Okay, subtract, so this area, side surface area of the bigger cone. Let's use A, B, C. Area of the cone A, ABC, cone area of ABC, ABC. Okay, subtract the small cone. Let's use this point to be D, this point to be E. Subtract the area of the small cone, pi R1. Sorry, here is R2, R1. Then this thing is L1, L1. Then you can do, so what do we get? So A of the thing. So this is pi R2. You can replace R2 L1. L1 is, you can replace L1. So solve for L1. We don't want L1. L1, solve for L1. So this you get R1 L1 plus R1 L, which will be L1 R2. So L1 move terms, R2 minus R1 will be R1 L. So L1 is R1 L over R2 minus R1. Okay. So this will be replace L1 by R1 L R2 minus R1 plus L minus pi R1 L1. Okay, so this will be pi R2. Now this is complicated. So R2 minus R1, commented on R1 L plus L times R2 minus L times R1 minus pi R1 L1. So finally, what we get is, you see, L R1 cancel L R1. So this is actually pi R2 L R2 over R2 minus R1 minus pi R1 L1. Oh, we need to replace, sorry. We need to replace L1. We need to substitute L1 by R1 L R2 minus R1, sorry. Yeah, so this is R1 squared L R2 minus R1. Then you see we get a common denominator now. So this will be, so we have better symmetry. R1 minus R2, R2 minus R1. This is pi R2 squared L minus pi R1 squared L. So this will be pi L R2 squared minus R1 squared over R2 minus R1. Okay, so finally this will be pi L R1 plus R2. Okay, pi 1. Okay, so if you do it more symmetric thing, so this is pi L 2 pi RL. Okay, here R is the area. R is 1/2 R1 plus R2. Is the area. Is the area. Area of the radius. Is the area of average radius. Okay. So it's more or less like the cylinder. So in this case, the form looks like the cylinder. Okay, so let's go back to our original question. Now, if you view this as straight line, if you can view this as straight line, so here suppose this is X, and this is x plus dx, x plus third x or something, x plus third x. Then the radius r1, the radius r1 is the function value at x, okay? So this is the height. The height is given by the function value, okay? The height is given by the function value, okay, r1. Now this is r2. R2 is the function value at x plus third x. If you use linear approximation, so this is, you know, fx plus f derivative at third x, okay, plus higher order terms, degree 2 terms, linear approximation. Then R2, if we choose third x to be small, then you find the arc length L. So the L, you know, the length of the generating line. L is the arc length of the curve. Arc length of the curve will be ds. Okay, L will be ds, which will be 1 plus f derivative squared times dx. Okay, so this gives the generating line. Okay, length of the generating line, and the radius, average of the radius, r1 plus r2 divided by 2. R1 plus R2 divided by 2. So R1 is fx. R2 is up to higher order. So this is fx plus f derivative x dx. Okay. So this is the R1, this is the R2. And then you put them together, you divide by 2. So we get an area form. The area form, then we get dA. Area form will be 2 pi r times L. 2 pi r times L. Then what we get is, you see, this will be what? Now higher order dx multiply dx just gone. Dx multiply dx. Higher order, just, you know, higher order. We just put dx times dx to be 0. Okay, so finally we get this thing, we get times dx times twice fx plus f derivative x dx multiplied by 2 divided by 2. So this dx, if you multiply dx, you cancel as 0. So you get actually this. Finally, the differential form will be, don't forget 2 pi. So this will be 2 pi fx f derivative squared dx. Okay, so this is the area form. So this is called area form. All the area element, or you call it the area element. Then we integrate the area form from the range of x. Then we integrate a, the area, which will be a to b dA. So this will be 2 pi fx 1 plus f derivative squared dx. Okay. Okay. So if you use Leibniz notation, so this will be a to b 2 pi y times that's right. 1 plus dy over dx squared dx. Okay, so this is the arc length element. So you can also use this a to b 2 pi y times ds area form. This ds is arc length form. Okay, let me stop here. Any questions?
You